Today we'll look at families of functions, transformations, and symmetries. We've looked at different functions before, and today we're going to mostly focus on our basic functions. Y equals x, the square function, the square root function, the cube function, the cube root function, and the absolute value function. Consider the function f of x. We don't exactly know what f of x is. We can talk about all the transformations f of x by looking at y is equal to a times f evaluated at x minus h plus k. These are, again, all the transformations to f of x. Okay, this also refers to a family of functions because since we can put any value in we want for a, h, or k, it'll get any transformation to the function f of x, so we call it a family of functions. If we think about the more familiar y equals x squared, then our family of functions here would look like y is equal to a times x minus h quantity squared, and then we'd add k. So this is the family of all the quadratic functions. So we're going to start by looking at what each of these things kind of do. When we look at a, we're going to see that it refers to a stretch factor or a reflection. H refers to a horizontal shift, and K refers to a vertical shift. So what we're going to do again is break each of these down. Let's start by considering these horizontal translations. For our horizontal translations, I'm going to, just for simplicity, think of H as a positive number. That way when we talk about our translation, if we have y is equal to f evaluated at x minus h. This refers to a shift of the function f of x to the right. So in this specific example, I think about what value would make this quantity x plus h 0. And we'd have to put in a positive h. So it means that we are going to shift the function f of x to the right by h units. Can say it, and I can't seem to be able to spell it right now. It shifts the function f of x to the right by h units. If we consider the function y is equal to f evaluated at x plus h, this refers to a shift of the function f of x to the left by h units. Okay, and again on this one, I tend to think about some of these things by thinking about what value in the parenthesis of x would make that 0. So what we're going to do is we're going to start by looking at some graphs. I would like you to graph y is equal to x squared. And then on the same graph, I want you to also graph y is equal to x minus 2 quantity squared. And then last but not least, we'll look at y is equal to x plus 1 quantity squared. So go ahead, take a moment, and start at least graphing y equals x squared. Alright, so I've started by graphing our function y is equal 2x squared. If you need to pause and finish doing that, you're welcome to. You could again make an x and y table if you needed to. But we worked on graphing this last time. This is a graph I want you to be familiar with. When we go to look at the blue function, y is equal to x squared minus 2. If you think about the value of x, that would make this quantity 0. It's x equals 2. So that tells us that this shifts the graph of our quadratic right 2 units. So some of you might be thinking, well, I need to make another xy table. If we know that it's going to shift our function x squared to the right 2 units, then you can say this point at the origin should now go right 2 units. This point right here at 1, 1, we're going to move it right 2 units. So it would go there. And you can kind of continue that process with each of the points you've already drawn. Whoops. Got a little enthusiastic right there. So then we connect everything with a smooth curve. And this is our function f of x is equal to x minus 2 quantity squared. And then last but not least, if we look at this last function in the black, x plus 1 quantity squared, think about the value of x. That would make this inside equal to 0 when x is negative 1. When we graph a negative, we go left. That's why we shift left. We're going to shift the red graph to the left by 1 unit. Okay, again, you don't need to make an xy table, but you can take every point and move it left 1 unit. And we're going to continue finishing moving all of our points to the left 1 unit. Now we can connect them all with a smooth curve. I'll try and keep using color today. I would encourage you to do the same in your notes. So that's just some of the horizontal translations that you'll see. The next transformation we're going to look at, in fact, are the reflections. And when we look at these reflections, we always want to specify which axis. So if we have the function y equals negative f of x, whoops, this is a reflection across of f of x across the x-axis. So y is equal to the opposite of f of x is a reflection across the x-axis. If you think about what this is saying, right, f of x really represents a y value. So when we add this negative, it's saying make all the y values opposite in sign. So in order to sort of think about what this is, we're going to graph f of x is equal to the square root of x. And I'd like for us to look at g of x is equal to negative the square root of x. And let's think of g of x as being the red function. We're going to graph these on the same grid. So go ahead, get your graph paper ready, and then we'll start graphing. Alright, so if we go to graph f of x equals the square root of x, remember this had a domain from 0 to infinity. So, whoops, wrong color. X could be 0, the square root of 0 is 0. The square root of x equals 1 is 1. The square root of 4 is 2. the square root of 9 is 3. And we saw that this looked sort of like a sideways parabola. Try and make your graphs a little more accurate than I just did. Close enough. Okay, that's f of x. And let's actually label that f of x. F of x. Now we want to graph our function g of x. So what this is saying is take each of the y values and make them opposite. So notice that x equals 0, 0, the opposite of 0 is still 0. When x is equal to 1, we had a y value of positive 1. The opposite of positive 1 is negative 1. At x equals 4, our y value is 2 for f of x, so g of x says take and make it the opposite. It's really just this reflection over the x-axis. So when we put the square root and the negative square root together, it looks like a sideways parabola. But if we were just looking at the opposite of the square root of x, it would just be this red graph. And we can see again that it was like we folded something over the x-axis. Our next transformation referred to the stretches and shrinks, or stretch and shrink factors. So if we have a times a function f of x, this will stretch the graph of f of x if a is greater than 1. And then if we have a times f of x, well, it'll shrink the graph of f of x if a is between 0 and 1. So 0 is less than a is less than 1. Notice none of these are for equals 1. If it was equal to 1, it wouldn't be very interesting because there is no stretch or shrink factor. Also notice that none of these values of a refer to negative values. Well, we've already talked about negatives previously. If we had a negative value, that would have referred to a reflection, and then we'd have to apply a stretch factor as well, or a shrink factor. So on the same grid, I would like for us to look at f of x is equal to the absolute value of x. I'd like for us to also look at g of x, which is equal to 3 times the absolute value of x. And last but not least, I'd like for us to look at h of x is equal to 1 over 3 times the absolute value of x. So we're going to look at each of these on the same grid so we can really see what's going on, just like we have with the previous ones. So go ahead, get your graph paper, and then I'd like for you to at least graph your absolute value of x function. Alright, so you can see that I've gotten my graph paper and I've graphed our absolute value of x, which I've shown is f of x. Now we want to think about what is happening to the function g of x. Well, we can look at some of the specific points on f of x and think about those in particular. And what g of x does is it takes each of those y values and multiplies them by 3. So notice at 0, x equals 0, our y value is 0. 0 times 3 is still 0. When x is 1, for the absolute value, the y value is 1, and we would multiply that by 3. That's our new point for the function g of x. When x was 2, the absolute value of 2 was 2, and then we'd have to multiply that by 3 to get g of x, which would give us 6. Okay, and we can do the same thing. If x was 3, we'd get a y value of 3 for the function f of x, and the stretch factor is saying multiply that by 3 again. And we could do the same thing on the left side with -1, with -2, and -3. So here is our function g of x. Notice that it looks a little bit skinnier, like someone stretched it out tall like they would if it was taffy. And then for h of x, this one it will do in blue. So we'd take the absolute value of x. So notice I'd have this point at 0. With the absolute value of x at 1, did you guys notice that my y value was 1? So I'd have to multiply that by 1/3, and we'd get a fractional value. If I look at when x was 3, the absolute value of 3 is 3, and then we'd multiply that by 1/3. So my y value would be at 1. And then I'm going to pick specifically what the absolute value of 6, because I'd multiply that by 1/3, my y value would be 2. And we can do the same thing on the negative side. And hopefully you see here, it looks like someone tried to squash this one flat. So we typically will call this a compression, and this would be a shrink factor because it made this graph grow a lot slower. Okay, that's it for our stretch and shrink factors. The last one we'll look at are vertical translations. Alright, with our vertical translations, again here I'd like for you to think of k as a positive number. So if we have a function y is equal to f of x, and then we were to add a number k plus k, what this does is it shifts the function f of x up by k units. Similarly, if we looked at y was equal to f of x, but we subtract k, then this shifts the function f of x down by k units. So, just so we can sort of see what some of these look like, let's look at f of x equals x squared. Whoops. F of x, we'll try this again. F of x equals x squared. And then I'd like to graph g of x is equal to x squared minus 4. And then let's look at h of x, which we'll say is x squared plus 3. We're going to graph all three of these on the same grid. Go ahead, get your graph paper ready, graph x squared, and then we'll start from there. Alright, I've got my graph paper. I'm working on getting my graph of x squared. Okay, my graph's not looking super great, but could look better, it could look worse. There's f of x. So if we look at x squared minus 4, what this is going to do is it's going to take each of these y values that we used as key points to graph it, and we're going to shift each of them down by 4 units. So my new y value right here, when x is 0, I don't get 0, I should get -4. I'm going to take this value at 1 and shift it down 4 units. I'm going to do the same on the left. This y value when x was 2 gets shifted down 4 units. And I can do that for every single key point you essentially use to make this graph. Again, not my best looking graph. A little bit better. There is g of x. So it was like I picked the entire function f of x up off the graph paper and I shifted every point down 4 units. Again, the hint that I sort of do is I pick each of the key points that I used for f of x and I think about how I need to move them. For h of x, we're going to consider our function f of x, but now we want to take each of these key y values and move them up 3. So for example, at 0, I'm going to move it up 3. When x is 1, I'm going to move it up 3. When x is 2, I'm going to move this point up 3. And if we do that, that's going to give us our new graph. So here, when x was 2, I'm moving that up 3 units. There's my new y value. And if I were to move this point when x was 3 up 3 units, it's going to be off the grid, so I'm not going to do it. But this was our function h of x. Okay, that's it for some of the translations. So what we'll do in class is we'll look at a handful of different examples where I will ask you guys to identify the transformation, and then we'll specifically talk about multiple transformations in class and try to graph them. Before we do that though, I do want to touch on that very quickly. So with multiple transformations, again, we'll look at some graphs of these, but we always want to graph things or do our transformations in a specific order. So the first thing that we always want to look at is, did we have a horizontal shift? If we did, apply it first. After you've checked your horizontal shift, the next thing that we're going to do is we're going to deal with that A. So deal with any stretch, shrink, or reflection factors. And once we've done that, the last thing that we are going to look at is applying any vertical shifts. So if you think about what each of these represented, our horizontal shifts, we had our generic function y was equal to a times f of x minus h, and then we added k. So a was our stretch or shrink or reflect factor. H was our horizontal shift. And K was our vertical shifts, up or down. Horizontal shifts we had left or right. Okay, so the horizontal shifts was what was represented by H. Our stretch, shrink or reflection factors were represented by the letter A, and then our vertical shifts were represented with that K. So if it helps you to think that you need to hack and go in that order, then that's something, again, that I would think about. So in class, we will look at just trying to identify what was happening with the transformations, and then we'll look at some examples of graphing multiple transformations. You're certainly welcome to look in your book at some of the examples there as well. So the last thing that I want to leave us with is a discussion of symmetry. So symmetry is something that we will use later when we go to graph polynomial functions and rational functions. So it's going to be important to see if you guys can identify even functions, odd functions, and then it's also possible for us to have a function that's neither even or odd. So here's the idea with even functions. If you evaluate f at x, and you also evaluate f at negative x, if they are the same value, then your function is even. And this has to hold not just for one x, but for all x values. If a function is even, so you can think of the quadratic on this one, right? If we plug in f equals 1, we'd get 1. If we plug in negative 1, we get negative 1. With x squared, if we look at negative 3 and x equals 3, you get 9 regardless for your y value. Even functions are cool because they are symmetric about the y-axis, meaning that it looks like we could flip the graph over on the y-axis. If it was paper, we would fold it on that vertical axis and we'd see each side matched exactly. Okay, we can also talk about odd functions. So here's the thing with odd functions. Odd functions, if you evaluate f at negative x, it almost has the same y value as f of x, but it's opposite in sign. So f of negative x is equal to negative f of x. And again, this is for all x values, at least all the x values in our domain. And if a function is odd, then it's symmetric about the origin. And symmetry about the origin is a little bit weird, but you can essentially think of doing a 180-degree rotation at the origin. X cubed is sort of the graph that I think about when I think about symmetry. And then last but not least, a function might be neither. Okay, so that's one we don't want to forget about, because when we go to classify functions as even, odd, or neither, then we need to keep in mind that they don't have to always be even and they don't always have to be odd. All right, let's look at a couple quick examples and then we will call it a day. So with these examples, we are going to classify them as even, odd, or neither. And I'm going to move these up, even, odd, or neither. So if we want to determine the symmetry of these, which I apparently cannot spell, determine, there's an N there. The symmetry of, we're going to look at this first. And the first one that we're looking at is f of x is equal to negative x. So to decide if a function is symmetric, we need to look at f of x. So here it was negative x. And we also need to evaluate the function at negative x. So we need to think about what is the opposite of a negative x. And in this case, we get x. So to decide if it is even, odd, or neither, we are going to compare these boxes. Do you guys see how they're off in sign? So because these are off in sign, it matches our odd functions. Notice you get one value and it's opposite of the other one, which would make this function odd. Okay, if we look at f of x and f of negative x, if you look at their end answers and they're simplified, notice that they're off, every term is off by a negative sign, which makes it odd. Okay, again, let's look at some other ones. So let's determine the symmetry of, and in this one, our second example, we are going to look at, comment dog, stop. Let's look at f of x. For second example, we are going to determine the symmetry of the function f of x is equal to negative 2 times x squared plus 5x. So in order to do this, we need to evaluate the function at negative x. Negative 2 times negative x quantity squared plus 5 times negative x. When we simplify this, we square the negative x first, so that's just positive x squared, and we have to multiply that by negative 2, and then we'd subtract off 5x. So just like before, we want to compare f of x, which I'm putting in a blue box, to f of negative x. Do they look exactly the same? If they do, that would make it even, but we can see here that they are not exactly the same. And since they aren't exactly the same, we can rule out that it's even. So the only thing we have to decide, is it odd? Well, to decide if it's odd, notice the first term's the same as the first term, and the second one is opposite in sign. Not every single term is opposite in sign, so it's not odd even. Not odd either. Not odd, not even. That makes it neither. And our last example that we are going to look at is f of x is equal to x to the fourth minus 2x squared. Even, odd, or neither. So again, to decide, we need to evaluate the function at negative x. We would take negative x, raise it to the fourth power, and subtract off 2 times negative x raised to the second power. Well, negative x times negative x, that's positive x squared. And then we'd essentially multiply it by a negative x, so we'd have negative x cubed. And then we'd multiply it by negative x again, so we get positive x to the fourth. And then when we take negative x and square it, that's like an x squared. And we want to compare f of x and f of negative x. Here they look exactly the same, which is what we said would happen if our function was even. So that makes this an even function. Hopefully these examples kind of clarify what that means. Again, we will look at some graphs and talk about what even and odd look like graphically in class.